Hello, my name is Pi. Today I would like to explain about some of the formulation you need to know before you get to use my toolbox. It's very important if you understand the formulation very well, and you should be able to set up this formulation based on the problem you're given. So let's start with some dynamical systems. These dynamical systems have to be in state space formation. So let's start with some notation. We call this x. Okay, x, you can use vector hat, but assume that this x is a vector that depends on time as well. Okay, so we might have a bunch of states. So I mentioned n. Okay, does it make sense? So we get x of t is a state. It's called state. Okay, and if you evaluate x at every point in time, okay, we call state trajectory. Okay, does that make sense? So x of t is called state trajectory. Okay, because it depends on time. Of course, you can plot x against t. That's fine too. Now you have u. Okay, the dimension is m. It's called control input. Okay. Of course, u of t is called control input trajectory, and so on. Okay, does that make sense? So now your dynamic system x dot, which is change of x in times, can be written or has to be written in this form. A function can be linear or non-linear, doesn't matter. That depends on the state, the input, and the time at that particular moment. Okay, so if you don't have this t term as an explicit term, it's called time invariant system. Okay, if entire f here is linear, okay, in terms of x and u, then it's a linear system. Okay, assuming that you can come up with this. Oh, let's go through some example. Let's say that you have this precision table that can be modeled as a spring mass system. Okay, where y is the displacement. Okay, y double dot is basically the acceleration. So you have to be able to turn this into a system of first order differential equation. Sometimes it's not easy, but in this case it should be relatively easy. And this one is a linear system as well. So you set up the first, it's a second order system, so you should have two state variable, x1 and x2, and x1 equal to y and x2 equal to y dot. Okay, so if you take derivative, x1 dot will equal to y dot, and in this case y dot is equal to x2. Okay, next two dot will be equal to y double dot, and that's nothing more than solving this equation. So y double dot will be equal to 1 over m, okay, minus ky, but y, we say that y is equal to x1, so I'm going to use x1 here. So everything has to be in terms of x1 and x2, and so on, plus the control variable u. Okay, so now you can see there's a x dot here. Okay, this is our x dot equal to f of x, u, and t. Okay, this entire thing here, okay, is a function that depends on state x1 and x2, depends on u, and it also depends on t, but not explicitly. So this one is a time invariant system. Okay, so that's how you formulate this dynamic system. Okay, so we're done with this. Okay, let's talk about constraint. Okay, and this might be new to you, but let's think about some constraint that's useful. For example, we want to figure out the control policy, but the control policy have to be, let's say that we have the maximum control, u max. Okay, and it's the maximum amplitude. So both direction, assuming that we have only one control input in this case. So for this example, Okay, u only have one dimension. Okay, and we said that u, okay, absolute value of u at any time t has to be less than or equal to u max. Okay, it's a saturation in control input. So how can you write this in a nice form? Okay, we have to put everything in this form. It's called, okay, this form is used in my code. So if you can't write this in my code, you have to turn everything into this form. A function, a non-linear function or linear function that depends on x and u less or equal to 0. Okay, so let's change this together. So how can we do this? U less than u max, okay, and negative u less than u max, okay, and only thing you have to do, move u max to the other side, okay, and set it all less than 0. Okay, and this is a vector. Okay, not that hard. So entire thing here is h that depends on x and u. Apparently it doesn't have to depend on x explicitly. This function alone depends on u explicitly, and this entire thing less than 0. So that's how you formulate this constraint. Okay, the constraint is given, but it's not in the form that you can be used in the code. In the code you have to be able to write in this form. Okay, so you have to move things around so that everything else is on the other side of this inequality, less than or equal to. Okay, it's very important. So for this type of constraint, is called inequality path constraint. I use so inequality path constraint. I use some abbreviation here. Okay, I don't want to write an entire thing. So the reason why it's called inequality path constraint is because it is an inequality. Okay, it is a constraint, but it's applied to entire path of x and u. Okay, so if we have x at any particular time t and u at that particular time t, you should be able to write. You should be able to evaluate this, and this inequality have to hold. Okay, it has to be true. Okay. Of course, you have inequality path constraint. You might have this inequality path constraint. Okay, it can be written in this form: x. Okay, if you want to be explicit, you can say x of t and u of t equal to 0. Okay, for all t within the domain from 0 to capital T, which is the final time. Okay, so this is called equality path constraint because it's the equality constraint applied to entire path. Does that make sense? You don't normally see this, but people might come up with it. There's a lot of things to ask. You ask the entire path or the entire trajectory to follow this specific rule. Okay, the next thing that you can have is called equality terminal constraint. Okay, so equality terminal constraint. Okay, it's nothing more than a function, okay, that depends on the final time. So you have this state trajectory here, but you evaluate at final time, and you also add this final time to it. Okay, and you say it's it's less than equal to 0. Okay, oh, this one is equality, so this one has to be equal. Okay, equal to 0. Okay, for example, the final state has to be equal to 0. Okay, so this is one of the constraints that you can write, or you can say that the final times have to be equal to some of the set point, some desired point. Okay, so therefore this thing here is q of xt, capital T. Okay, does not depend explicitly on t. Okay, because you have this xt here. Okay, now the next thing you can have is called inequality terminal constraint. Of course, the same thing, similar things. Instead of equal sign, you will have less than or equal to 0. So you will have a bunch of constraints, and just have to remember, put everything in one side and let the other side be 0. Okay, not that hard. Lots of programs require you to do this. So let's move on. The last thing. Okay, so let's look at Bowser form. Okay, so Bowser form is basically a formulation for cost function. So you have this cost j that's equal to integral from 0 to t, and you have this capital L of x, x of t, u of t, and t dt. Okay, plus capital M x of capital T and capital T. So L here is called Lagrange term. Don't get confused with Lagrange from Lagrange multipliers, different terms. Okay, it's not the same thing. And this M here is called Mayer's term. Okay, so just think about it. This means that the cost function depends on some term that's integrated from 0 to capital T. This is the final time. Okay, so you integrate it. Let's say you want to minimize the accumulated controls, you know, the field or whatever. You want to minimize it, then you put in this Lagrange term. Or sometimes you don't care about this term, so you can move it and make it 0. And then you say that you want to evaluate the final condition, right? This is the most important thing sometimes. So you say that, okay, I put everything in Mayer's term, but both of the term combined is called Bowser form. Okay, Bowser form. Okay, so there's a cost function. Okay, if I evaluate this with some arbitrary u, then I can't guarantee it will be minimum, but of course that's the whole thing, because u star, which is the optimal control policy, will be equal to argmin u, okay, of j of u. Okay, and this j is a function that depends on u. Okay, so I can put entire thing here, you know, replace it here, but I just want to write it short. But of course it's subject to multiple constraints. The first constraint that we talked about is the dynamic constraint. Okay, of course relationship of x and u has to hold. Okay, so this one is dynamic constraint. Okay, now we talk about path constraint. Okay, so what are these path constraint? Path constraint g, okay, of x t u t equal to 0, h of x t u t less than equal to 0. Okay, and of course this one is equality path constraint, and this one is inequality path constraint. This one is q. Okay, x of capital T equal to 0, or x of capital T less than or equal to 0. Okay, this one is terminal constraint, only evaluate at final time t. Okay, so you have to figure out how to minimize this cost function in this form subject to all of these constraints. There's a lot of things to ask, but it can be done. Okay, numerically it can be done, and for special case it can be done analytically as well. That you should be able to figure out what is the function L, okay, what is the function M, okay, what's my dynamic system F, okay, what is my constraint G, H, Q, and R, okay, what's my final time. The thing is that the toolbox should be able to come up with control policy even though you don't know what is the right final time. So let's say that I don't know what's the final time, but give me the time that it will give me the minimum J, the control. The toolbox should be able to come up with a policy that satisfies that as well. Okay, so here's the optimal control formulation. You should be able to understand each part. Okay, should be able to write it out. I will go with some example of how to translate the word problems to this kind of formulation. Thank you for watching, and keep in touch.